Thank everyone on behalf of the department and WTS and ITFU chapter. I know the weather is not, typical, but don't forget that we are going to rain season. Thank you that you stop by. We have another a few on the Zoom. Dr. Menendez is going to give a presentation. Jan is going to introduce, but I would like to apologize because miscommunication. We are not going to offer a coffee cookie or anything, during this presentation, for this presentation, okay? Yanni.
Okay. Good morning, everyone. Thank you so much for being here today, especially in a rainy day like this one. I would like once again to thank Dr. Monica Menendez for accepting our invitation and coming here today. So Dr. Menendez is the Associate Dean of Engineering of Graduate Affairs and Professor of Civil and Urban Engineering at New York University of Abu Dhabi. She is also the Director and Lead the PI of the Cities Research Center, and she's the recipient of a Distinguished Research Award for 2021. Also, her research interest includes multimodal transportation systems, paying special attention to new technology transformation sources. Also, Dr. Menendez, she's the author for over 100 peer-reviewed journal publications, and she has over 200 conference contributions as well. So with that said, Dr. Menendez, thank you so much once again for accepting our invitation. Please feel free to start your presentation.
Thank you everyone for coming here with the rain and on the first day of the summer semester. So thank you. And special thanks to Evangelos and Yanis for arranging this. Thank you very much. This is my first time at FAU, but I used to live in Miami 30 years ago. So this is, it feels like South Florida is home for me. So I'm very glad to be visiting this university. It's a very nice campus. So, okay, I need this. Today, I'm going to be talking about, I work in quite a few topics, a lot related to multimodal transportation, but data also. How do we use data in the cities to understand how people move, etc. But today, I'm going to be focusing on new vehicle technologies, and in particular, modular vehicles, and how do we leverage the emotion transfers within modular vehicles for better public transportation. Now, I understand public transportation is not the thing here in South Florida. I used to live here, so I know it'd certainly be much better. But, public transportation is way more sustainable than cars, right? From many different perspectives. It has a smaller environmental footprint and a smaller spatial footprint. So we can basically move more people in a smaller amount of space and with less resources. Then why isn't appealing in places like South Florida? There's a lot of traffic. I spent a lot of time today traveling from Miami here by car. So why are we still stuck to our cars if public transportation has so many benefits? Because it also has a lot of challenges, and challenges differ across cities, etc. But I'm going to be focusing today on 3 challenges that are quite prevalent in cities around the world. And I'm going to try to address those challenges throughout the presentation today. So first, the idea of bus bunching. I don't know if you have heard the terminology, but bus bunching is a well-known issue for quite a while. And the idea is that with the stochasticity in traffic conditions, etc., headways, or the time between buses, deviations in headways compound over time. So what you end up having is buses bunching together. So you have a lot of buses coming together and then no buses at all. And that presents an issue of reliability. Now, from the user's perspective, you also have the problem of unnecessary stops. Like if I'm going from A to B, I probably have to do 7 stops in the middle that I don't care about, but just because the bus is there. So compared to private cars, public transportation has an issue of speed, right? And last but not least, for today, you have to do typically transfers, external transfers. So if I'm going from here to here, I probably have to take a bus that goes here, get off the bus, either walk to another stop and wait, or even within the same stop, wait for another bus and then take it off. And that presents an issue of inconvenience, right? Or convenience, an issue of convenience, lack of convenience. So my proposal, or our proposal, is to use modular vehicle technology to address that. Now, I'm not sure if you are aware of modular vehicle technology. What is it? these are individual vehicles that can, or pods or units that can travel individually, or they can come together as a single bus or a single vehicle of higher capacity. The idea is that people can move between the vehicles while the vehicles are moving. So that's what I call emotion transfers. The capacity typically for this specific company is 6 people if everyone is sitting, or 20 people if everyone is standing. But there are quite a few companies that are working on this. Then the vehicles can split from each other or decouple and take different routes, or come together and form sort of a platoon within the same route, on the main route. This helps address a lot of the last vehicle mile problems. And there's a lot of studies about this, using this for on-demand transportation. All the cases that I'm going to be showing today are for fixed route public transportation or fixed route buses. Now, if I want to highlight the main features of this technology, their autonomy, the fact that these are autonomous vehicles, although they could have a driver. They're electric, so all the advantages associated with electric vehicles. They offer variable capacity because you can have one small pod or multiple pods coming together and creating a bigger bus. And emotion transfer between the pods, meaning people can move between the pods while they're moving, while en route. And for the presentation today, I'm going to be leveraging, in particular, this feature. Do you have a question or no? Okay, sorry. So the idea is to use this emotion transfer to address these 3 problems. And, for the reliability, I'm going to be talking about 3 different sets of operations or proposals that we have for the operations of public transportation. To address the reliability issue, I'm going to be talking about what we call bus splitting operations. To address the speed issue, I'm going to be talking about stopless operations. Bus that doesn't stop. Okay, I'll go over that later. And for convenience, I'm going to be talking about transferless operations. So I'm going to start with the reliability thing. So as I said, bus bunching is a recurrent problem in public transportation. We have known about it forever. There are many strategies to address it at the infrastructure level and at the operational level. Still, it's very recurrent everywhere. One strategy that we're using as a basis or as a benchmark is what's called bus stop skipping. So when the buses are late, you skip a stop. Now, theoretically, people have been talking about bus stop skipping for a while. Theoretically, it's very good. Practically, it's not, because when you skip a stop, the people who wanted to get off at that stop then have to walk back. And the people who were at the stop waiting for the bus need to wait for the next bus. So even though theoretically has received a lot of attention, in practice, very, very few operators use this. So what we propose in lieu of the stop skipping is bus splitting, because we can split now these buses into multiple units. So before I continue, I'm gonna sort of share some terminology that is gonna be useful throughout the presentation. The bus can have 1 or more units, right? By units, I mean the individual pods that I show you. And when they all come together, or even if a single unit is there, it can be a bus. Now, I'm also gonna divide the bus into modules. In this case, for this type of operations, it's gonna have 2 modules: the leading module, one in the front, and the trailing module, the one in the back. Each module can have 1 or more units. It can have 3, 4, whatever. But then that means that a bus needs to have at least 2 units, 1 per module, correct? So I have a bus, then a smaller portion is a module, and then the smallest unit is the smallest part is a unit. So the idea with bus splitting is that these modules the trailing and the leading module can couple and decouple, and one of the modules can skip a stop while the other serves that stop, and they recouple later, so they can do the operation many times, and that way they serve multiple stops in parallel rather than in series, right? And that saves time and addresses the issue of reliability. So let me show you with a graphic more or less how it works. Let's assume you have a bus coming there, and that is running late for whatever reason, traffic conditions or whatever is running late. So before it gets to the stop that I'm gonna call the control stop, that's a stop where it splits. It doesn't always have to split, right? Like this is if it's running late or something. The passengers must rearrange. If you're going to a control stop, you move to a trailing unit, to the unit in the back, to a green unit. No, I'm sorry, to a blue unit. If you are going to the next stop, you move to the leading unit. The rest of the people can distribute themselves any way they want. So then these two models, they couple. The trailing unit stops at the control stop while the leading unit continues to the next stop. They sort of serve these stops in parallel and they recouple later. The blue unit stops here very briefly just to recouple and they continue. So showing you this with a time-space trajectory. I'm not sure how familiar everyone is with time-space trajectories, but I'm just gonna go briefly over them because I'm gonna show them multiple times. So in a case of no control scenario, if I wouldn't do anything to the buses, okay, so time-space trajectories, I have time in the horizontal axis and distance or space in the vertical axis. So this is the route of the bus. So the slope of a line here sort of indicates speed, right? Distance over time. Here is when the bus stops. It's not moving, so the speed is 0. So in a case with no control, when I don't do anything, they have the red bus and the green, the dashed line will be the theoretical or the expected trajectory for the green bus, for the next bus. But here it goes lower than it should because whatever, there was an accident, traffic. So by the time it gets to stop number 2, there are more people waiting. This is typically what leads to bus function. So the dwell time there is a little bit longer because you have more people boarding and alighting, right? Or more people boarding at least. And then even though it catches up on speed afterwards, every time it gets later and later. The next bus, the blue bus, by the time it gets to a stop, there's less people waiting because the other bus just left. And so these buses start coming together and getting farther apart from the other buses. That's called bus bunching. In a case of stop skipping, what you would do is that the bus, as it's getting to stop 2, it skips stop 2. So very good for keeping up with the schedule, very bad for the passengers. So from the operator perspective, it makes sense. From the user perspective, it's awful. What we're saying is in bus splitting, by the time it gets here, the leading unit continues to the next stop while the trailing unit stops. And then they catch up later on. So how do we model this? We use a discrete macroscopic model and compare 3 types of operations. What if you have no control at all, or conventional bus system? What if you have stop skipping, which we're using as our benchmark, and bus splitting, which is what we're proposing. And the goal of what we're doing is to minimize the headway deviations. Headway deviations increase the waiting time tremendously. And the waiting time is worse than the vehicle time in terms of passenger experience. So that makes the public transportation system very unappealing. So we want to minimize the headway deviations, the main absolute percentage error of the headways. And we also want to minimize the total passenger cost, which is waiting cost, plus in-vehicle cost, plus walking cost in the case of stop skipping, because you have to walk back, right? And our operations are very simple. Our policies are simple. We are not focusing on the control part here. These are the basic operations that the simplest operations that we could think of for this type of system. They're non-predictive, so I don't know what's going to happen in the future. They're distributed, so each bus is making this decision individually. And they're myopic, meaning you're not looking at what's going on around you or how this is going to affect you. So these are very simple. Anything that you do better will improve the results, right? So this is like the bottom line that you can get on the results. Any better control strategy would just give you something better. And the idea is that if the bus is running a little bit late, more than certain threshold times the headway, then you execute the policy. In the case of stop skipping, is that you skip the stop. In the case of bus splitting, you do what I mentioned before. And then we have to model the vehicle dynamics, meaning the stochasticity of travel times, when the vehicles couple, when they decouple, how do they do it, etc. We need to model also the passenger dynamics. How are people arriving at the stops, where they're going, when do they have to board on board, and the interactions. If the bus is full, people cannot board the bus and they have to wait for another bus at the stop, etc., or how people move within the buses when they're decoupling. So we're doing, we're modeling the vehicle dynamics, the passengers, and the interactions between these two systems. I'm not gonna go over all the details, but these are the set of parameters that we use. And then we vary many of those. And we use to test this, a realistic quasi-homogeneous route, but the segment lengths, the arrival rates, the lighting probabilities, were all drawn from normal distributions. And, we estimated fleet size based on the demand. And we ran 500 iterations for each scenario, just to see to capture well the variations on the scenario. I'm going to show you results for 1 hour after some warm-up period. And we start the system from equilibrium. So at the beginning, we say, buses they're sticking to the headway, and we just let it run, or let it run. In the case of a non-controlled scenario, you will see that buses start deviating from the headway soon after. In the other cases, you will see. So these are, again, the time-space trajectories that I mentioned before, but as a result of the results of one specific scenario, right? I can show you with this one specific scenario. And in the case of no control strategy, you see that the buses, after certain period, we had a warm-up period, they start bunching together. See, this is bus bunching. So you have very long periods when no buses come, and then buses come together. In the case of stop skipping, you see a little bit less bus bunching. The black dots are the stops that are skipped. Now, from the operator, this is fine. From the passengers, every time this happens, passengers have to walk or wait longer. Bus splitting, the dots represent the control stops every time I split the bus. And what you can see quickly, more or less from here, is that both the stop skipping and the bus splitting reduce the bus bunching compared to the original scenario, right? Now, these are the results for that specific scenario. And I'm showing you for one specific scenario to illustrate what's happening. But these are, the insights are the same for all the scenarios that we tested. And I will show you that in a second. So here, this was our main objective, the mean absolute percentage error of the headway. And we do much better than the no control case. And here, you see that we do slightly worse. I'll show you this because this is not actually truth. I'll explain this in a second. But we reduce the average waiting time, the in-vehicle time. There's no walking time in our case. And then the average travel cost, and what we call the bunching overhead. The bunching overhead is the actual travel cost divided by the expected travel cost. So we say that it's almost zero, meaning there's no cost. Bunching is not really affecting the system as much. And we also reduce the cycle length. By reducing these deviations, you manage to keep the cycle length shorter. And then that allows to reduce the average load per bus, how many passengers, and this is good because you have buses that are less full. And the fraction of full buses, which is also good because every time you have a full bus, people cannot board and have to wait. So that was for single scenario. And here you can see that bus splitting consistently outperforms the two other options. But this is for a bunch of scenarios. So I'm changing the demand. And for each of these demands, I run 500 scenarios. And you see here it's a box plot with all the average and all the deviation or all the results. Now, what we have here is the mean absolute percentage error of the headway. This is what we want to reduce. We want to make this as low as possible. The blue line is the no controls for different demands, right? High demand, low demand. The blue line is I don't do anything, the conventional case. The green line is the bus splitting. Now we have two orange lines for the stop skipping. Why? I show you the results for this orange line, for the continuous orange line. That is the headway as seen from the operator. My buses are, the operator is tracking the headway. This is normally how you calculate the mean absolute percentage error of the headway or the deviations on the headway. In this case, it's not the proper way of doing it. The dashed line is as seen by the user. Why, as seen by the operator, is not the proper way of doing it in the case of stop skipping, because you can have an extreme case where all the buses are traveling with perfect headways, but they never stop. So from the user perspective, you spend forever at the stop, right? So this dashed line captures that. From the user perspective, every time a bus skips a stop, my headway is twice as long, right? Or whatever, is longer. And so the number that I showed you before was from here, but if you look at the actual user experience, you see that bus splitting does much better always. The same axis, y-axis, but here I'm testing, and the same three lines, the same colors for the lines, but here I'm testing the control threshold. That means how aggressive I am in starting my control option. So this means 1.1 means a 10% deviation on the headway, and I already start, meaning I already skip a stop or I already implement the stop split, the bus splitting. This will mean a 200% error or deviation, right? Again, in all cases, the green line is better, it's much lower than the other two. That's not surprising. But what is important is that the biggest differences happen when we start the policy as soon as we see the first deviation. Even with the small deviations, we start implementing this policy because there's not a lot of cost to the policy itself, but holding and not doing it, withholding that policy leads to much worse, to a performance that deteriorates quite fast. So headway deviations, what you can see here is that headway deviations are significantly reduced with bus splitting. These are just the components of the travel time, average walk time for different demands, average in-vehicle time for different demands, average walking time for different demands, and then the combined average of those, the weighted average of those. And as you can see, bus splitting does better across all dimensions. It leads to the lowest travel times across every dimension. Yes?
So with our current system, if there's nobody at the bus stop to flag the bus down or nobody on the bus queues that they want to get off, the bus is allowed to skip the stop. But does the stop skipping scenario account for even if someone flags the bus down, the bus still skips?
So on the first part, this happens with some operators that differs across cities. Some operators allow buses to skip a stop if there's nobody at the stop and nobody flags that stop in the bus. Some operators don't, and the bus always stops there. The first one is a better option, right? But that implies that the buses have triggers and that you can recognize people, you can see people at the stop, etc. Some operators allow that to happen and some operators don't. The stop skipping as a policy is independent of that. It's just saying, even if you have people on board, and what happens, and this is why it's hardly ever implemented, because what happens is that if you have people on board that wanted to go to stop 2 and that stop 2 is skipped, they go all the way to stop 3 and then they have to walk back. And if there are people at the stop waiting for the bus, they just have to wait for the next bus. So that sucks for the people. Okay. So remember what we wanted to do was lower the headway variability. And with this, we can lower it by up to 50%. We can also reduce the cycle length, which is good because I have a better use of the resources. If the buses can go faster around, with less buses, I can serve more people. And the average number of passengers per bus can go down by about 15%, which is also better for the convenience of for the experience within the bus. The waiting time can go down. This is the biggest one because bus bunching leads to very high waiting times. So that's the issue with bus bunching. It's not so much in vehicle time. So this goes down by up to 60%, while in vehicle time goes down by up to 15%. And this is compared to a no control scenario, right? I'm talking about the no control, in comparison to a no control scenario. So overall, this is good. But if you remember the pictures that I showed you at the beginning, the time space diagram, bus bunching is reduced, but it's not eliminated, right? And the problem is that bus splitting helps when the buses are late, but if the buses are early, there's nothing you can do about it. So in public transportation, another common strategy, and this one is implemented in many places, is what is called bus holding. When a bus is early, you might have what is called control stop, where you stop the bus and you hold it there until it catches up with the schedule, right? Not every stop is a control stop because you need to have the space, you need to make sure that it doesn't, affect traffic or affect other buses, etc. But you might have one or more control stops, or maybe every stop is a control stop. It depends on the operator. But bus holding is something that is commonly done in practice. So this is why it's important. If the bus is late, when I do the bus splitting, I sort of catch up with the original trajectory. This was my desired trajectory. When I do the bus splitting, I can do better. But if the bus is early, this is my original trajectory. I end up with bus bunching, over time, and I cannot control it. The bus splitting doesn't help. So what we said was, let's combine bus holding, which is normally done in many places, with bus splitting. And I'm not going to show you all the results, but I can tell you you see, you have a little bit of bus bunching here with bus splitting alone. This is exactly that scenario when I put together bus splitting and bus holding. And I'm only using, in this case, one control stop, which is the first one. The more control stops you have, the better you're off, right? Because it gives you more flexibility, basically. So anyways, you can see that not only reduces bus bunching, but also reduce the numbers of black dots, meaning the need for bus splitting, right? So when I put these two things together, I eliminate bus bunching to a very high degree. And we tested this with a real route in China with a lot of data, and it was always the same. And we changed a lot of stuff, and it always performed very well. So in general, bus splitting combined with bus holding can eliminate bus bunching almost completely. And this drastically increases the reliability of public transportation systems, which was the issue that I was bringing up at the beginning. So with that, I'm going to move to a second set of issues, which is speed. And I'm going to be proposing stopless operations. Now, compared to cars, you lose a lot of time just because of all the intermediate. As a public transport passenger, you lose a lot of time because of all the intermediate stops, right? To address that, some operators offer express buses. These are buses that only stops at a specific, stop 1, 5, and 27, whatever. The issue with that is accessibility, because then if you don't live next to one of those stops, or you're not going to one of those stops, you have to wait longer, and longer walk times also, because you might have to walk longer just to make it to a stop that has where the express bus goes. So how do our operations work? Again, okay. So here we're gonna propose what we have to coin it, so it was easier, because then I'm gonna use this for the rest of the presentation. We call it SLAM bus. Oops, sorry. Stopless autonomous modular bus, right? The autonomous modular bus is what I showed you before, but now it's a stopless because it doesn't stop. I'm gonna have now two models. Again, the models. Okay, so the models can have any number of units, more than one unit or more. Before I had leading and trailing. Now I'm gonna have a main model and a service model. That's the name. And the idea is that the main model is gonna move throughout the system without stopping. And the boarding and alighting at the stops is going to be relegated to a service model. That's going to go stop, and then it's going to catch up with the next bus. So this is like a train that is non-stopping, and then you have a piece of a train that goes to a stop and then catches up, etc. And what I do is before I was serving two stops in parallel, now I'm offering two services in parallel: the travel part for the through passengers, and the dwelling part at the stop for boarding and alighting passengers. And these two things are happening in parallel. So we save a lot of time. So just to give you an idea how it works, the bus comes together with the main model and the service model, these two parts at the top together. As I'm approaching a stop, people who are gonna get off at that stop need to move to a service model. Anyone else should move to a main model. The service model detaches or decouples and goes to a stop. In the meantime, while the main model continues, to the change in speed. In the meantime, there was another service model at that stop that had been waiting there since the last bus passed and had been serving the boarding passengers at the time. This one leaves the stop and catches up with the main model and then continues until the next stop comes and you repeat the process again and again and again. You basically have one sort of train moving around and one model that catches up with that, another model that catches up and leaves. So in terms of time space diagrams, this is how it would look like. This is the main bus. And these are the models that go from one bus until it catches up with the next. And we're putting changes in color just to show you that it goes from one bus to the next one. A traditional bus would do this, the dashed line. Our SLAM bus is doing this. And what you can see is that the cycle length of a traditional bus will be this, and the cycle length of a SLAM bus, it's this, so it's much shorter. So your in-vehicle time is much shorter, so your speed is higher as a passenger. We model again this with a macroscopic, discrete macroscopic model, and we compare two strategies, a conventional bus and the SLAM bus, which is what we're proposing. Now, our goal here is to minimize the passenger travel cost, which is the waiting cost and the in-vehicle cost, right? And we also want to minimize the fleet size required, how many pods we have, right? To serve a given demand. And, you know, the operations is what I described before. The main bus bypasses each stop while swapping the service pods. Sometimes I have very busy stops. And then the service pods or the service model doesn't have enough capacity to hold all the passengers that want to alight or that will board. In that case, I will stop the whole bus there. Now, these stops, we call them stops for the whole SLAM. They can be scheduled or unscheduled. A scheduled is a train station. Everyone is going to a train station, or it's a hospital or something. And then you have a lot of demand going there always. So my bus always stops there, the whole bus. Unscheduled is suddenly I get a lot of passengers at that stop, or a lot of passengers that want to alight at that stop, and they don't fit in the service model. So I will stop the whole bus there just this time. I don't do that often, but this time it makes sense to do it. These are, again, the parameters I'm using. We're looking for realistic, we use a realistic cyclic bus route, but I had all the stuff drawn from normal distributions as before. We do 100 iterations because there's not that much variance. So we don't need 500 iterations. And I show you the results for 1 hour after some warm-up period. And I'm going to compare two types of operations, conventional and SLAM. In both cases, I'm going to be using the pods, the modular units. In the conventional, I'm just going to put them as a bus, as a normal, as a bus of bigger capacity. Now, I'm going to have the same number of pods on both. Every time I compare a scenario, it's going to be the same number of pods. But that doesn't mean the same number of buses, right? Because I'm going to have more frequent and smaller buses here, less frequent and bigger buses there. But the total number, the fleet size, in terms of number of pods, is going to be the same. And then I'm going to be looking at different combinations of pods, number of pods per bus. Okay. This is how a conventional bus would look like. And this is how SLAM would look like. So to start with, you have, this is steeper than that because you don't have the stops, right? So the steeper line, the steepness of the line means the speed of the vehicle. Here we have one, in this specific case, we did one scheduled stop, which is the first stop, or the last is that's the first. So this is a scheduled stop. So you see the bus always stops there. This here is because of randomness, and it's an unscheduled stop. So, and I know it's unscheduled because sometimes it stops and sometimes it doesn't, right? You see that? Just because of the randomness, this is for one specific scenario. We did many scenarios, and in other cases, we have more unscheduled stops, etc. This is just one. But what you can see is that the speed is higher, but also the head weight are more constant. So it's also addressing the reliability issue that I mentioned before with the busmanship. So SLAM typically outperforms conventional bus services in terms of speed and reliability. These are the results for that scenario, for that specific scenario. And just to show you that with SLAM, I have 5 pods per bus. That means less buses, right? Remember in SLAM, I also have pods that are stationed at the stops. And that is not that efficient in the sense that these are units that are sort of stopped there. And that leads to a longer headway typically for SLAM. However, the savings in average cycle time are so large that overall, the travel cost is, the longer headway leads to a longer waiting time, but the savings on travel time are so large that the average travel cost goes smaller, even though waiting is worse, it's weighted more than in vehicle time. So SLAM leads to significant travel cost savings, and this is for this scenario, but this is true for most of the scenarios that we saw. Here you see the average in vehicle time and the average waiting time for different demands. We have 4 lines because these two, orange and blue, represent 2 conventional services with different number of pods per bus. Blue means 3 pods per bus, more buses because you have smaller buses. Orange means 4 pods per bus, bigger buses, less frequently. And these are for 2 configurations of SLAM. In all cases, SLAM does better than this in terms of in-vehicle time because the cycle lengths are shortened tremendously, right? And for people, that's you don't have to stop in the middle. Waiting time is a different story. And for some SLAM configurations, the system does quite badly. So what is important here is that time savings are apparent for some, but not for all configurations of SLAM. And I'm gonna go over that in a second. This is kind of the average travel cost, which is the combination of the 2 previous costs. And this is the cost savings offered by SLAM. This is the best SLAM service, which in this case is the red, over the best conventional service, which in this case is the blue, right? Now you can see that as demand increases, the cost savings increase over 20%. But at some point, if demand becomes too high, the cost savings start decreasing and they can become negative. This happens because if the demand is too high, the service model is not enough to hold everyone that wants to alight on the part, and I need to make a lot of unscheduled stops. And when I start making a lot of unscheduled stops, it becomes sort of a conventional service in terms of speed, but then it's less efficient because I have the service models waiting there, right? So I have less models moving around, but so I'm losing speed and I'm not gaining efficiency in terms of capacity. So for very high demands, it might not be good in this case, right? Now, I could address that by increasing the fleet size. So this is if I use a fleet size, so the same fleet size for both conventional and the other one. So basically, the thing here is time savings can be very significant if the fleet size is sufficient, if I have enough pods. At some point, if the demand is too large and I don't have enough pods to serve that demand, then the service conventional outperforms SLAM. Now, when it's feasible, total travel times can go down by 20%. It's great. This is total travel times. So that's waiting plus in vehicle. And waiting goes up, so in vehicle actually goes down even more. And the cycle length can go down by 35%, up to 35%. Now, the cycle lengths go down because there's no duals, there's no stopping, right? And we know in urban areas, you tend to have a lot of stops. So a lot of time is wasted at the stops. The total savings in cycle length pretty much depend on your, like the balance between travel time and stop time, because you're removing a lot of the stop time. Not all of it, because you can have some stops, as I said, but you're removing quite a bit of it. So that's why. So overall, SLAM eliminates dwell times, and it increases the travel speed between any to stop to values that are actually comparable with that of cars. This also increases the reliability of the system as long as the fleet size is enough for that demand, right? And then another thing that I need to highlight here, and I don't have time to go over all the details, but not all configurations, as I show you, not all configurations for SLAM, even with the same fleet size, not all configurations are optimal. So it is worth exploring what is the right configuration for that specific case, for that specific setting, not case, but setting. And with that, I move to the last thing, which is convenience and transferless operations. So no one likes to transfer buses. If it's raining, it's even worse. And what many bus networks do is, what many people do is design bus networks that minimize transfers. But that typically lead to very complicated routes. And still, you cannot eliminate transfers completely because it's impossible that all buses will serve you for all origins and destinations in a single line, right? So we are proposing these transferless operations, and we are doing this by leveraging in-motion transfers, which is when people are moving and the things are between modules. And then we allow the modules to couple and decouple so they can change routes. I'm not talking about on-demand transportation. I'm still talking about fixed route systems. This, by the way, still increases the speed and reliability. So it builds on the previous concepts and is still addressing two previous issues. So now here I'm going to show you two examples. One is a feeder and arterial, and the other one is a bus rapid transit. And I'm going to try to go relatively fast. The feeder and arterial, the idea is that I have an arterial that is served with a SLAM service, the same as before, but each stop at the arterial has a feeding zone where you have passengers moving to that. And in the previous case, I had the service modules for SLAM just being stopped there. Now I'm going to allow those modules to move around while waiting for the next SLAM, dropping passengers and getting passengers from this area. So rather than having the modules just sitting there, I'm going to have them moving around like shuttles. So before I had a main and a service model, now I'm going to have a main and a shuttle model, because that model is not going to be stopped there. It's just going to be moving around. So let's say this is arterial. You have the main model and the shuttle model. As they approach, again, passengers coming to this area move to a shuttle model. Anyone going to another area stays on the main model. The shuttle model detaches, and the other shuttles that were around sort of come and attach, and then you start the system, the process all over again at every stop. And we call this shuttle SLAM. Pretty much the same thing as before. I compare with the conventional service. The idea is to avoid external transfers and to minimize waiting costs, in-vehicle costs, and transfer costs. I have the SLAM operations for the arterial, where I can have on-schedule stops and scheduled stops, the same as before, exactly the same as before. But then for the feeder service, I just have a conventional stop, like a conventional service, right? Where you stop at every stop. Why? Just because it was easier to model and we were focusing on the overall concept, but there are many other alternatives to this that will be better. Now here, the headways must be carefully synchronized, because I need to make sure that these people do this, the shuttle does this, but by the time the SLAM arrives, it's already there. So we put a buffer time there as well to make sure that this happens. But you need a lot of synchronization between the systems. We use a realistic bus route. Now we use a deterministic environment just as a starting point. The homogeneous demand among the zones and no intra-zone trips. So there's no people traveling within the zone, or at least we don't care about them. When comparing with the conventional service, again, we make sure that we have the same number of pods, even though that means different number of buses. And we look at the optimal shuttle SLAM configuration for every scenario. These are graphs of the waiting time, in-vehicle time in the arterial, and in-vehicle time within the zones for conventional and for shuttle SLAM as a function of fleet size, the number of pods that I have, the total number of pods, and the demand here. So the colors, the green is good, low. The red is bad, is high. So if I look at the travel time, in-vehicle travel time within the zones, it's pretty much the same for both cases, because in both cases it acts as a conventional service where you stop at every stop. For the in-vehicle time in the arterial, and the waiting time, shuttle SLAM does much better. This is where you shine, right? And that reduces the overall trip cost. This shows you the actual savings of shuttle SLAM compared to conventional. So Y will be, okay, so this is negative savings, so conventional is better, blue, up to 20% savings. Now, the gray area, that shows an area where this combination of fleet size and demand, with this combination of fleet size and demand, total SLAM is feasible, conventional is not feasible. And when I say it's not feasible, it means your fleet size is not large enough to carry everyone. This little black square here is the area where it's the combination where conventional is feasible, but SLAM is not. It's, so overall, total SLAM outperforms conventional bus services for most cases, and it has a larger feasibility area, which is great. It goes without saying, but you have no external transfers, and the travel times go down, the total travel times go down by up to 20%. Okay, so the next case is the BRT. BRT stands for Bus Rapid Transit System, and these are transit systems with high capacity and very frequent buses, but the lines tend to be very sparse. And so if you have a grid system, this will be the city. You don't have lines very often, right? They're sparse because these are high frequency. It's like a metro but with buses. You typically have dedicated infrastructure. The yellow dots represent in this specific, this is just an illustration, the intersections between two SLAM lines. The white dots represent normal SLAM stops, and these are just terminal stops. And let me quickly explain how it works. Now, this is the most complicated case because my bus has 4 modules. From back to front, a service module, central, a right and a left module. Why? Because people transferring lines don't get off the bus, they just get off their module. They transfer their module, and their module transfer between lines. So some specific pods transfer between lines, people don't have to get off the bus. And the way it works is you have the whole bus here, service, central, right and left. And as it is approaching an SLAM intersection, people who are going to a right move to a right module, people who are going to a left move to a left module. And then they move like this, and the ones coming from here catch up and they reform the bus. This gives you more or less an idea of a very simple diagram. The sort of path that each model takes. The service model is the one that stops at every stop. The central model is the one that follows that line from the beginning to the end. The right model is always turning right, always turning right. And it doesn't matter if it's 2x2 or a 27x27 grid. And the left model does the same thing, but always turning to a left. And we call this a SLAM BRT. Again, what we want to avoid is external transfers and minimize the waiting costs and vehicle costs and transfer costs. The complexity here is the synchronization of the buses at the intersections. And we had to put some buffer time, and we actually have to stop the buses right after the intersection at the next stop to catch up there. I'm not going to go into the details, but this is the complexity comes in there. And for that, we assume that there's dedicated infrastructure. BRT typically have dedicated infrastructure, because otherwise it's impossible to keep that level of synchronization, like if buses are getting caught up with traffic, etc. So this is pretty much the same as before, but now we have a lot of parameters because the problem is way more complicated. And here I'm showing, again, for a combination of demand and fleet size, this is how many pods I have and different levels of demand. I'm showing you just the best configuration. Blue is conventional buses. And these are different configurations of SLAM. The numbers indicate how many pods or how many units in service, in central, in right and left. So here I have 2 right to left, 1 central, 1 service, for instance. So the bottom line is this blue area where conventional is better is because SLAM BRT is not feasible, because it's not enough to hold it. As long as SLAM BRT is feasible, it's always the best combination. It always outperforms conventional. And it typically does so with the smallest number of pods possible that hold that, that are enough to carry that demand. So when feasible, SLAM BRT typically outperforms conventional bus services. And here you see the savings. So again, this area, there's no savings because this area is where SLAM is not feasible. But for the rest, SLAM really outperforms, or the savings can be quite significant. There, again, bottom line, no external transfers, and total travel time savings of up to 35%. So, as a summary of this third concept, shuttle SLAM and SLAM BRT can significantly increase the convenience of public transport services by eliminating external transfers. They're also at the same time increasing speed and reliability. The issue here is finding the right combination or the right configuration for SLAM and making sure that the fleet size is large enough, especially in the case of BRT. So with that, I show you how to address these three challenges. One question that I typically get asked is about how people move within the models and whether that is feasible or not. If you have two models, I think it's fairly easy. You know, in many public buses, as of to, it depends on the city, but in many cities, you get on through the front door and you get off through the back door, right? So you have to move as to get off the bus. So if you have only two models, it's not that complicated. You move to the back model if you are getting off. You move out of the back model if you're not getting off. When you have more models, like the last thing, it's more, you know, like that. There, it's complicated. But then I found this video from Next. Next is a company that I've been working with. I mean, I don't get anything out of them or anything. It's just that they're sharing a lot of their specifications for the technology. It's an Italian company, but there are many Chinese companies that are now doing this. And they had this video for Dubai because they're trying to sell this in Dubai and Abu Dhabi. And they had this video. The difference is that they have drivers. They did a pilot study there, a pilot test without drivers, but apparently Dubai wants drivers now. So they put drivers in the, I don't know how to put this video. How do I do this?
I don't know. No.
No, my computer would do something, but.
I can click.
Idea how vehicles mobile and then how people would transfer it. So now this is telling you how to move with your vehicle. In the case that we're proposing, it will be easier because the vehicles would always have the same order and you can even color code them, right? So if going left, it's always orange, and going right is always red or whatever. But it would take some getting used to. I agree with that. But anyways, the idea is that, you know, I show you the basic examples and you can build on them a lot, but you can use this modular vehicle technology to increase the reliability, the speed, and the convenience of the system, which is, these are three of the biggest issues that public transport face nowadays. We're also working on how to increase accessibility by having it more flexible rather than fixed routes, more flexible routes. So increase accessibility, the flexibility of the system, and make it more personalized. So addressing your own needs for travel. The idea is to develop efficient public transport systems that make travel sort of seamless and provide a flexible and personalized experience from the user perspective, which is a big difference with cars, right? Cars are very, for you, you do the trip is however you want to. Public transportation is not like that. But we believe the future, it's a multimodal transportation, and modular buses are part of that ecosystem. They're not the only thing in that ecosystem, right? We're trying to integrate this with other modes of transportation, with other technologies, etc. But the idea is to use this as part of that ecosystem. And with that, I finish my presentation. I need to really thank this guy. He was the PhD student who did all that work. He's not a PhD student anymore. But all the stuff that I talked about today is on those papers. And yeah, so he was the one that did everything they can. And thank you for your attention. And if you have questions, I'm sorry, just went really quick, but.
Yanni,
If there are no any other questions, I have one quick question.
Yanni, before you ask, that's good.
That's why I said if there is no any other
He didn't
question.
even ask.
Sorry, I have a very quick question. In the shuttle slam, we have a different part. I'm curious if, for example, we have an accident or disruption for one segment, what happened about the whole system?
Yes, so it's fair. What happens when we have any sort of disruptions in the system? So we typically, we put buffer times, and our buffer times were not super small. So it's a cost that we're embedding into a system. So it's not as efficient as it could be, right? The synchronization. If the delays go beyond that buffer time, yeah, there are many other ways of doing this. So right, ours is what I propose today here is the basic, where you leave this slam and you catch up with the next one. But you can do that every 2 slams. You leave this slam and you catch up with 2 slams after or something, right? And the next slam, the next slam catches up with 2 slams after. So that will give you more buffer time. So there are other ways of doing this. We also looked at the fixed route in the feeder. It could be an on-demand route. And if you have an on-demand route and you have some delay issues, you can skip areas of that, right? So if you have real-time information. As I said, for all the examples that I gave, we looked at the most basic example because anything else will be an improvement on that, right? But yes, that is a concern. And that's why for BRT, we're saying you need to have dedicated infrastructure because otherwise that synchronization will be impossible. But yes, synchronization is the biggest issue for the last 2. Yanis.
Yeah, okay, now it's my turn. No, I had one question because I'm working on something similar in
Okay.
freight mobility.
Okay.
But a difference I saw is that at some specific point when this each individual convoy is traveling, passengers might be allowed to travel and change those
Yes.
individual pods. How safe is it actually for them? Because let's say this convoy travels and then a sudden break happens.
Sure, but this is the same as in a bus. In a bus, I'm walking and the bus is moving, right? In a normal bus, I will walk while the bus is moving. So it's the same concerns. We have been talking a lot to the manufacturer, and they have they give you the range of speeds at which is the coupling can happen or the decoupling can happen or people can move, etc. But in terms of walking, it's the same as a normal bus, right? You walk. This is not for freeways, right? So the speeds are not.
I thought we increased the chances of something to happen because we actually encourage passengers
To walk.
To walk.
Sure.
Because normal bus, they don't have to do it. I mean, only
But-
at the time of the, the decoupling.
Well, it depends on which system you're talking about, but in some systems, there's a lot of walking because the stops are very frequent and you're moving while the bus is, and if the bus is full, you cannot wait until the bus stops to move. So I'm saying, if you come from a developing country or whatever it's called, you would know, you move a lot while the bus is moving just because you need to make it to the stop, to the door. But yes, that is fair. They have safety, they have ranges for the speed of the bus and the speed at which, but that's a fair concern. Yeah, I don't have a response for that, except that, if accidents happen.
Yeah, of course. And I also have another question. I mean, in the last model that you showed, the last scenario, there was like a left turn
Yeah.
and a right turn both. In the United States, there is this thing that on red you can turn right. So there is like a continuous.
Sure.
Let's say. Is this the same case in?
No, so this one assumes, no, I'm not assuming any priority here, actually. It doesn't matter what you do, the buses will not be able to, all models will not be able to get to the other side at the same time, because if this one has green, this one doesn't have green, or this one doesn't have green, right? So this is why we put there, again, a buffer time, which makes the system less efficient, but it's necessary. And we actually stop the bus at I didn't go over the details, but we stopped the bus right after the intersection at the bus stop. We need to assume that there's enough space at that bus stop to stop the bus and wait for all the models to catch up. And we give either 1 or 2 cycle lengths for that to happen. So if there is turn on right on red, great, that model will catch up faster. But the one from the left will have to wait for the left green, right? So that will have to wait 1 cycle or 2 cycles or half a cycle or something. Yeah, so it's independent of that. The more priority that you have for public transportation, the less the buffer time, the better it's gonna be. But we're not assuming we have a very high priority or anything. We do assume dedicated infrastructure, so dedicated lanes, because in the absence of dedicated lanes, that synchronization level throughout all the intersections will be impossible. But here, there's a lot of calculate, you need to make sure, to have this level of synchronization, the problem becomes much more complicated, and you have much less flexibility in the way, in the headways that you can have, so the frequencies of the buses, etc. So it's much more cumbersome. The more priority we have, the less we need to put those constraints, the less constraints we need. But we assume that we didn't have any, basic priority.
And the very last question.
Sure.
You said that at the last scenario, it's important to identify those ideal, let's say, platooning partners.
Yes.
So I guess this one also increases the complexity of the problem.
Sure.
So
Because
that you have like 2 goals, like one to, let's say, minimize the stops, and then another goal to minimize the cost or something like this.
yes.
Are we actually talking about actual optimization, like exact solution, something like this, or
No.
we're talking about?
No, we didn't do a super proper optimization. I mean, we do have an optimization, but we're not going through, it's not an optimization problem, the way that we're going about it. Because there's many things involved, and it was just easier. Like our focus, we hadn't seen any of these operations before, and this is why we didn't focus on the control part. We're now working on the control part, and which is linked to optimization. But we didn't focus on any of that because we wanted to just look at whether we can bring any benefits with the most basic operations, right? After that, we can look for thresholds of application and the specifics of the control. We're now working with the control person to actually fine tune many things, which can be done much better than what we did, much better. So we're working on that now.
But I think even these results, they are encouraging because
Yeah.
so they're not optimal.
Exactly. So this is what I'm saying. Like even in the lack of, with the lack of an optimal approach, or for the shuttles, the question about this, I said we use a fixed route just because a fixed route with this is easier. But if I were to do it on the mine, it would be much better. It's just a much complicated modeling thing. And this guy had to graduate as well. So his PhD had limited time. He worked on a lot of stuff. So we said, okay, we do stop based. You can do much better. We haven't done it yet.
Thank you so much.
Okay.
I don't know if we have any other questions.
Okay.
If there are no any other questions, I would like to thank Dr. Menendez once again for coming here and
Well.
presenting her work. Also, we prepared like a small gift for you. That's from FMRI, the Freight Mobility Research Institute. We have like a T-shirt for you.
Very
It's,
cool.
yeah.
Oh, okay.